In this video, we want to talk about, in general, what could be algorithm analysis. And also we wanted to emphasize the non-recursive algorithm analysis. First, let's check the general algorithm analysis. Given a code, we want to check how efficient this code could be. We consider two things, runtime and memory space. We see for these two things, when we made the measurement for these two things very similar actually. So this reason, in this study, we only explain the method for runtime. And for the runtime part, we check how long the algorithm takes in terms of the size of the input, or how fast the input grows with input size. Why we care about input size? The reason it is, if the input size is small, doesn't matter how this algorithm could be, and it can quickly finish. Only when the input size becomes huge, in that case it is, we have to predict how long it could be. Is something wrong with running and running never stop? Or because the runtime of this algorithm. So this reason we care about how long the algorithm takes and how fast this algorithm grows with the input size vary. Especially with corresponding to when the input size increases to infinity, how fast your algorithm could be. And usually we have two types of studies. One is called experimental studies, corresponding to you do experiments and check how many milliseconds it takes for input size 10, for input size 20, or for input size 100. And you wanted to predict that. You wanted to say, based on this data we collected, and maybe for 1,000 data points, and the input size is 1,000 or 1 million, and what could be runtime. Okay. The second method, which it is theoretic study, let's first check for the experiment study. Let's use 3-sum as example. The 3-sum is a problem formulated as given n distinct integers. We want to find out how many triples sum to exact 0. For example, here we have 8 numbers. We want from among all these 8 numbers, we want to find out all the triples. Sum them up, the result is 0. For example, if you pick up 30, pick up negative 40, then in that case, the 10, if you add them up, then in that case, the sum up of these 3 numbers is 0. And then you can see if you choose 30, negative 20, then if you choose negative 10, then the results of the sum up of these 3 numbers is 0. The algorithm for this 3-sum problem corresponding to this part of code, we have less loops, right? So you scanned numbers in this list. You check each number by one each number. Then you want to select the second number, and you have to scan each remaining number again to check this is combination of these 2 numbers can find the third number, which can make sure the results of the sum up of these 3 numbers to be 0. So we use I as a count variable, scan it. Then we use J as count variable, scan from I plus 1 through n. We choose the second number, or we just list. We iteratively check the combination of all these possibilities, and we use count variable k and count from j plus 1 through n, and if these 3 numbers add together is 0, we count the triples, count up the number of triples. Then we return number of triples. When we run the code, you may find out based on the number of n we choose in this list, and this could be the runtime with the corresponding seconds. We want to predict if we know we have for smaller number through the 8,000, we want to predict for 16,000. What could it be if the input size is 16,000? What could be the runtime? Then we put them in the plot, and you may find out this plot the curve is in this way. It's corresponding to if n increase to huge number and the runtime increase will be bigger than what you increase as the number of input size. And sometimes we can use log scale and to visualize that. And based on different problem and the relationship between the input size with the runtime may appear in the different patterns. For example, this is a linear pattern corresponding to when your n increase, proportionally the runtime will correspondingly in the same scale increase. And take a look at this one. When the input size n increase, we see that in the runtime, the increase of runtime is smaller than the scale of increase of runtime, smaller than the increase of input size. And take a look at this one. This is the C, plot C. We first take a look at plot B. We see this is linear. Then we take a look at plot A. We see the scale of runtime increase is far smaller than scale of input size increase, right? Then let's take a look, plot C. We see here the scale of runtime increase. It is far beyond, is more than the scale of input size increase. Although this experimental results, we take a look at the plots and it looks like beautiful, and we see they do have some problem, and because it really depending on the situation of your computer, how many process was running in your computer, and also it depending on the program language you choose, the compiler you choose, and hardware and software and of your computer. So this is the reason people like to use the theoretic analysis and to check, give algorithm, what could be the efficiency group of each algorithm can cast into. You may ask why we care about the efficiency group, because when we compare the two algorithms, we want to check who is more efficient. We consider the scalability. And here we see they use a high-level description of the algorithm instead of implementation, characterize runtimes as a function of input size, taking into account all the possible inputs, allowed us to evaluate the speed of algorithm independent of hardware and software environment. Here we list all the advantages of this theoretic analysis. Let's take a look what it is this theoretic analysis. What is the specific method we use for this theoretic study? Time efficiency is analyzed by determining the number of repetitions of the basic operation as a function of input size. Since we have to check how long it could be, we want to use mathematical function to formulate that, and we want to group the algorithms based on the runtime scale, especially based on the scale ratio, the increased scale ratio between runtime and input size. Because based on the plots, we can see they have different patterns. We want to see from the theoretic study, can we also find out these patterns? And the result that's true. This is a way to classify the algorithm efficiency, classify the algorithm groups, and also it's the way we check which algorithm it could be better than another one. And here we need to check, give you a code, we have to say this runtime depending on what. So we say that depending on basic operation, depending on the frequency of a basic operation. This function count is Tn function counter for both. First, check what is the basic operation, the operation that contributes most towards the running time of the algorithm. So it means it should related to the input size. And this is COP corresponding coefficient, the execute time for basic operation. Cn corresponding to capital Cn corresponding to number of times basic operation is executed, corresponding frequency of this basic operation in the given code or in the specific algorithm. Tn is a runtime for basic operation. So give you code, we want to find the formula of Tn, which is the aggregated frequency of basic operations. Or you can treat this runtime as the count of or the number of basic operations or the number of statements. Sometimes it's because we wanted to find the scale, increase scale ratio, right? So we really don't want it so precise because it's grouping, it's cluster. We want to put the algorithm in different groups. We care about the scalability. Let's take a look at an example to see what is basic operation here. Search for k in at least n items. In that case, this is the problem. And input size which corresponding to n items. And the algorithm here, you have to check each item in the given list and compare this item with k. If they're mapping, then we found it. So the comparison, it is the basic operation, right? So it's just see some main operation which related to input size. Then we want to use the majority operations as the k to find out what is group this algorithm efficiency can cast into. Okay, so the empirical analysis of time efficiency and follow these steps. First, we need to select a specific sample of inputs, use physical units of time, and analyze empirical data. For some algorithm, efficiency depends on form of input. We say first, we runtime depending on the input size, depending on the frequency of basic operation, and which is related to input size. And the second thing it is sometimes the runtime also depending on input instance. If you give different input instance, the runtime may appear quite differently. So we see the order case corresponding to the specific input instance. In that special case, in that special input instance, and your code take more compute efforts, right? And we will see example later. The best case corresponding to some specific input instance, which when we run the same code for that instance, it take computer take less efforts. So it's best case runtime. So it's corresponding to minimum runtime over all the input instances. And what's the case corresponding to maximum runtime of all the input instances of them same size n? average case corresponding to the all these input instance, and we get the runtime for each input instance. We sum them up, get the average. So in that case, in the average case, we check expected number of basic operations, consider as random variables and some assumptions about the probability distribution of all the possible inputs. Let's take a look at example, sequential search, right? As we discussed in the several previous slides. And search for a given value in a given array by sequential search. The input is include two. One, it is array A, 0, and -1, and search K. And we already know the basic operation, which related to input size n, in this case, which is a comparison, right? And you may see you have two comparisons here. Can we use this both? We see here I smaller than n, which is the I is a count variable, and smaller than n is easier to make sure this code can be stopped, can be finished when you scan all the elements already, right? So in that case, it is doesn't matter how this n could be. This should be have on runtime in this part. But this AI make a big difference. If AI happen equal to k, in the case of I equal to 1, in that case you only need to run for, if this AI equal to k, right? In that case you just need to run for, just evaluate this condition, then that's it. You do not need to go to the loop, you just skip the loop, and you quit the whole while loop totally. So in that case, that's really the best case, right? The best case, it is O1 corresponding constant, and worst case corresponding to On. And currently we didn't explain what is this O corresponding to, and we will explain that this is corresponding to constant. O corresponding to your runtime were upper bound by n, upper bound by some function. Okay, so this is the average case, and for the other case which corresponding to in the whole list, you cannot find the element which is equal to k, and in that case you have to scan all the elements. So the worst case is On. It means the runtime were upper bound by this n. And for the average case, we check. First, we assume the probability of k in A is p. K has uniform probability in any position of A. The probability for k not in A is 1 minus p, and such that expected counting if this k, the search k, is in the A, and such that it could stay in the different positions from 1 through n. Right, and each is one depending on the position they do have. They need to have multiple steps. So it could be have I is the number of steps and times the probability, and which is corresponding to p. So it means it's p times I sum up over, it should be p times I.